Okay, so we continue with this quest for Oscar. And it's a pleasure to introduce Ana Peón, that she's going to talk about the geometry of the nilpotent cone.
Yeah, thank you. Thank you. It's great to be back to my mathematical home on this great occasion of Oscar's birthday. Many thanks to the organizers for inviting me. So I'm one of Oscar's children. There are many of those. And I'm more precisely the fruit of an incestuous loop with Luis. So I'm not going to get into who's the mother and who's the father. I could have two moms to that, or that's up to them to choose. But for the subject of my talk, I've chosen a subject on which Oscar has contributed with numerous results. So I will be speaking about the nilpotent cone. So let me introduce the objects. I'm going to denote by M, X, and D the moduli space of Higgs bundle on a Riemann surface. The genus and basis theorems of these two. Self-fixed invariants, I won't mention them much. I'll just consider them to be fixed. So this is the wrap, and this is the. So let me, for notational purposes, just say what the objects are. These are the close points are vector bundles or Rankinen. And degree D. And that we say holomorphic section of the endomorphism bundle, the 25 section. And then you take these up to us. Okay. So the nilpotent cone is a crucial object in the geometry of its moduli space. So there we have a Hitchin map, which is a completely integrable system, which assigns to each Higgs bundle the characteristic polynomial of the Higgs. This you probably also know very well. So this is a point in a vector space. And the generic fibers are really nice, well behaved, there are a billion varieties, but there's one extremely singular fiber, which is the so-called nilpotent cone, the fiber over zero, that has very intricate geometry. So first of all, it's non-reducible. It's reducible. It has different irreducible components. It's non-reduced. So I'm going to, whenever I speak about one of the reducible components, I will be considering the underlying reduced scheme. So I won't be worrying about the multiplicities for the purpose of this talk. So if I say reducible component, I mean the underlying scheme, underlying reduced scheme. Okay. Now, there's a rather good, still not complete, understanding of the irreducible components, which can be given in terms of a C-star action. So inside the nilpotent cone, there are some special subsets that have appeared, which are the irreducible components of the C-star action.
It's very visible.
What's that? You can't see that well?
Behind
What's not visible, the red color?
red color.
Really? Okay. Well, I only have red and green. I'm afraid the green is going to work. Let's see. How about green? Is it better? Okay. So I'm going to denote by curly fi. So we have the cell variety of fixed point of the moduli space is easily seen to be contained inside the nilpotent cone. And it has some irreducible components. We just parameterize by some set I. And it turns out that these Fi can be seen. They have different modular interpretations, and they are in particular moduli spaces of chains. And this is a subject that Oscar has studied in multiple occasions. And there's a very nice result from 2018, together with Bradlow, Goffin, and Hanlo, where they are able to parameterize the irreducible components in the smooth moduli space case. And give a lower bound. In the non-smooth moduli space. Okay. Now the interest, our interest, Kristen and myself, in the nilpotent cone stem from a different object, but it's very much related to the global configuration of the nilpotent cone, and I'll try to make the point later on in the talk. But we became interested in the wrongly called Drinfeld conjecture, which involves other objects called wobbly bundles. So let me find maybe before I move forward. So what is a wobbly bundle? So a vector bundle is wobbly if it admits non-zero nilpotent experience. So more precisely, the definition by Lomon was the opposite. So he defined very stable bundles and through their stable in particular. So very stable bundles would be vector bundles with no non-zero nilpotent Higgs fields. It's not true that a wobbly bundle is very stable. And but in particular, one can assume the extra condition that E is very stable. So in this particular case, so suppose one of the components of the nilpotent cone I've forgotten to say is the moduli space of vector bundles. Right, so these are identified with a given vector bundle together with a zero Higgs field. So suppose one of the irreducible components has a pair where the underlying bundle is stable. If one takes the C-star action, it goes to infinity, one hits one of the upper fixed points on front. It's not, I mean, it's pretty clear that this is also in particular a fixed point component, right? Because multiply 0 by lambda, then it's takes 0. Now, if one flows down with the opposite weight, so T goes to 0, when E is stable, then the limit is going to be E0. So wobbly bundles, when they are stable, can be identified with those bundles that flow down from an irreducible component that's not the moduli space of vector bundles. And why do I insist on this aspect? Well, it's important to understand why Dernfeld's conjecture should be true in general. So what does the conjecture say? Let me keep the name as well, anyways. It says that the wobbly lockers in the moduli space bundle. So these are the semi-stable system. There exists no zero. Still. Is of pure dimension one, namely any irreducible components that's for dimension one, so it defines a divisor in the modular space. The wobbly bundles are geometrically interesting objects in their own right, without any reference to very stable bundles. Now I should mention that Paul has some appropriate where he proves the conjecture using Fano geometry. So our construction is more constructive. Sorry for the repetition. So it allows also to understand to study the singularities, for example. In particular, how different irreducible components interact with their embedded components and so on. And also it's more nilpotent focused. This is nice also with Hal's approach. He doesn't need to refer to Higgs bundle necessarily, but in order to understand the role of global bundles in this global configuration, it's also useful to see in this case. Okay. Right. So what is the what is the idea of our proof of for now in rank 3 anyway? Okay, so take one of the irreducible components, it will flow up to some fixed point component. And one of the, so if we have some pair where the underlying bundle is stable, we are going to suppose that it flows down to let's assume this is smooth. So these ranges are often called Fi minus bar, but let me just call it C. Suppose this is smooth inside. Then because C is Lagrangian, the tangent space at E0 of C will have the dimension of the modular spacing. And also because it's Lagrangian for the symplectic form moduli space, then let's see if I write it correctly. If we have a Higgs field, then the orthogonal space to the Higgs field for the symplectic form will contain the tangent space C intersecting with the modulus. Okay, so in particular, if there's only one Higgs field flowing down, then by smoothness, this needs to be a divisor. So provided there's an integral manifold, then we're done. We have a divisor. So what's the strategy to summarize?
We're using rank 3 here.
No, nowhere.
No.
This is no rank 3. I mean, it's the construction then that requires rank 3 to make sure that you have everything. That's where we need rank 3 because we know there were reducible components in that case. So the strategy is just to look for vector bundles with a unique nilpotent Higgs field. So the variance. And for Glitzel. So this is where rank 3 is very important because it's really not. Any questions so far? Okay, so let me say that when one reads a unique nilpotent Higgs field, I'm just going to spoil here and say that there's real net, or sorry, Oscar, but I love the green color.
I can see it. I don't know the people behind.
Oh, can the people behind see? Yeah. So the Brinner up here gives a way to stratify spaces of stable bundles with so many sections, and we use that crucially in our construction. And for after because the work of many people is important, starting with Sundaram, already in 86. So, I mean, most of the things we need are in his work already. But there's also Ruto Teixidor. And work from Brambilla Langford. Seminar work. Okay. Let me move on to the rank 3 case. I'm going to explain how to construct irreducible components of both the nilpotent cone, and this is already studied by many people on open layers. So to mention some. In rank 3, it's really important to mention Goffman and Rohans. where they studied they compare the hard narrative and then the building to be rule specification. Then there's also work by Hansel and Gotham. Their thesis. And I'm certainly forgetting others, but those are there. Maybe one. So in rank 3, there are a few cases, right? What nilpotent Higgs fields can one have? There are 3 possible orders. So either phi 0, and then we know what happens. We're in the moduli type of bundles. Could be that phi is squared to 0, and then the Higgs field has natural filtration. There's always a natural filtration, which is the iterated kernel filtration, and in this case, it's of length 2. Right, so E0 is the kernel of phi squared. E0 is the kernel of phi, and E1 is the kernel of phi squared. Or phi cubed is 0 and not square, and in this case, the iterated kernel filtration has E3. So in order to try and spot the Higgs fields, we're going to proceed by precisely looking at iterated kernel. These are the building blocks for nilpotent Higgs fields. So let me call Fi. Non-curly Fi will be one. So it's a graded piece of the iterated kernel filtration, where E1 is 1 and 0. Okay. Let's see how good. 20 minutes. Okay. So there are then 2 interesting cases, filtration of length 2. So what are the key features? We have that in this case. E is an extension of the following. It's a so E finds a Higgs bundle extension of the co-kernel by the kernel. So in particular, this is the same as a 0. F1 fuel of 0 has a section. So in cases where all graded cases are stable, which is not always the case, then we will be looking for stable bundles. In the Brill method method of some so rank 2 and a given invariant. I'll say what later. Okay, so to find the suitable invariants, there are dimensional arguments. So we want to spot irreducible components of the nilpotent cone, and by study the object I'm going to construct, one gets full dimensional schemes. And then when it's to check that these are all. All right, so now over these brilliant locus.
And so that is for any rank, no? I mean, you don't have.
Well, the only issue in different ranks is that you need some stability assumptions on the on the graded objects.
Yeah, but you can have the twisted brilliant theory.
Yeah, but you still need
Well, yeah. They don't need to be stable to have sexual.
No, you don't need them to be stable to have section.
You have to
But then-
keep it.
Okay, maybe we can talk later because how does the certification work? Really,
the
it's
same.
exactly the same. Okay. Okay, so right. So in this case, over the brilliant locus, one can construct a vector bundle, just parameterizing the sections, right? So given a bundle here, the 10 sections. So in the given bundle, this is not a vector bundle, it's a rational vector bundle. And then what does this one need to parameterize? Well, there's an extension of theta to I. Right? Okay, so the theorem is the following. There exists a rational vector bundle. Sorry. So I'm parameterizing F0 and F1. F1 and F1. 0. Okay. And the associated projective bundle is birational. And your reducible component. And all components with the generic condition that the heat still vanishes at order 2. Is of this form. Okay. So let me maybe mention so what is suitable? What are the invariants? The invariants vary in a range. Oh. There's this range, and wobbly divisors happen. When do they happen? Well, precisely when this bundle of sections is of rank 1. And this happens precisely when delta is between 0 and 2. So there's no one-to-one correspondence between the reducible component of the nilpotent cone and the wobbly divisors. More precisely, each irreducible component for each of the invariants contracts to a divisor. So by it contracts along one dimensional subspace. But for, say this is over to G means 2. for any other value of delta, the divisors define some subspaces of the higher, say, Moduli. So there are some badly singular points here at the level of the nilpotent function. Okay, so what happens for length 3? There is an interesting remark which corresponds to the existence of some privileged chains and co-chains in when one sees fixed points in terms of moduli of chains, and it is the following. So if I contain an nilpotent Higgs bundle, so this is the kernel of phi squared, and it also contains, or it defines, a nilpotent function just by taking the kernel and quotient it. Now, neither of these, I mean, it need not be that this is semi-stable or this is semi-stable, but what it's true is that either one, so one of them is always. And what this allows is to construct the nilpotent cone in rank 3, or at least these components given by iterated kernel filtrations of length 3 in inductive terms from rank 2 Higgs bundles, not bundles, but Higgs bundles. Say rank 3 from when the bottom cone in rank 2. Okay, so let's say this is case 1.
And
Yes.
very separate.
We use the function on E, that E is again.
Yeah, you need to assume if phi is semi-stable.
No, just E phi or also E?
No, if phi has to be semi-stable. It's enough. I'm not sure whether this is a rank phenomenon or it can be generalized. Actually. Higher rank. Well, it depends. I mean, if you're looking at the wobbly divisors, I'm going to assume that E is stable in general. At least for this strategy to work, right? Because in the semi-stable case, you don't need for the yeah, the Higgs field may not appear in the moduli space, even if there is an important. It's trickier. Okay, so this is an exact sequence of Higgs bundles. Say case 1 and case 2. So by duality, up to change in the moduli space. So it is enough to consider degree equals 1 and 0, because every modulus is isomorphic to either of these. On duality, that changes M3 lambda and M3 minus lambda, and it exchanges cases 1 and 2. Not hard to see. So it's enough to understand what happens in one of these cases. So I'm just going to say case 2. All right. Okay, so now what do we have? We have an irreducible component of the nilpotent cone in rank 2. These are classified by some invariants that it's been known for a decade. I'm going to take this invariant to be the degree of residual of 1, but I mean it could be they can different. So this is a component in the nilpotent cone of rank 2 bundle parameterizing Q0 and Phi0. And then I have I need an extra line bundle to parameterize the kernel. Yeah, I mean case 2. But there is an extra restriction, right? So in fact, I want for everyone 0K to belong again to realness relatives. This is somehow pedantic to write it like this, but this avoids distinguishing the symmetric spaces and the Picard varieties. I don't want to take the sections into account, just the underlying bundle. So I may just as well substitute this by different. Okay, so again, over this space, which we'll want to parameterize. Well, I need to have, in fact, I can do it in one go. The interesting thing here is that one can find a vector bundle that parameterizes 6 bundle extensions of a given complex. Of Higgs bundle extensions, which are given by the hypercohomology of a given complex depending on all objects in 0 and F0. Again, this is a rational vector bundle. So there exists a vector bundle rational, well, such that predictivization of is birational meaning reducible component. Of an nilpotent cone for satisfying or make all them irreducible component. Okay, so back to 0. Out of this one. And actually the form the invariance take is really pretty. So there's so now we need, we have two invariants. Um, one and two. So here I have delta one plus delta two equals 2.6. This line is 2 delta 2 plus 1 equals 6g minus 6. So the red area corresponds to reducible components of the nilpotent cone. I mean, there are some congruences to be satisfied. And then for wobbly components, the lines are 2 delta 1 and delta 2 equals 4g minus 4. And 2 delta 2 plus delta 1 equals 4g minus 4. So just some remarks is that outside of this square, which is it is false actually that so outside. So here we have one semi-stable, but here E1 is unstable. The underlying bundle is unstable, and the opposite happens when one takes this symmetric rectangle on the other side. Also, wobbly divisors here. There are more wobbly divisors than the one could expect to build from wobbly divisors in rank 2. So the area of wobbly divisors in rank 2 would correspond to this square. But there are many more than one can construct. Okay. So maybe in the 5 minutes I have left, let me try to mention what happens in what we know in higher rank, which is not a lot. So as Leticia said, there are a number of things that one can try to mimic. For example, filtrations of maximal length, namely filtrations where each of the rated objects have rank 1 are easier in some aspects. So ideally, what we would like to see is to have some sort of privileged object. Is it possible? So is it possible if one has an arbitrary? So ideally, two will say. One subchain, such that the corresponding container semi-stable. So what happens in rank 3 is that the hardness filtration of the Higgs field, so the stability condition can only be violated precisely by, at least in this case, can only be violated by the iterated kernels. So this is a particularly easy case. It's not at all clear to me that this can be generalized. It's also not clear to me how to compare the iterated kernel filtration and the Bialy-Tibby rule-like certification in an efficient way. So this would be one of the steps to take. And there's another difficulty that may be sorted through this twisted Bell-Letter theory, which is there's a very happy coincidence in rank 3, which is the fact that there's a duality between, there are components of type 2.1 and components of type 1.2, fixed point components of the nilpotent cone. And these yield wobbly divisors of type 2.1, say. So with iterated kernel given by rank 2 and rank 1. Now, so rank 2 and rank 3, sorry. In this case, the relation is by duality. But again, it's not clear how it's generalized in higher, and it's probably a more complicated scheme that I have right now no intuition. So I think I'm up, so let me stop here and wait for questions.
Are there any questions or comments?
Thank you for your talk. So recently, as you know, Hausel and Hitchin have introduced the notion of being very stable for not just for vector bundles, but for chains, the big points. Have you thought about the answer to this problem?
Yeah.
Precisely for some of these fixed points,
Yeah.
varieties, chains of any size or something.
Yes, yes.
Good. And what is, do you have some answer?
So the answer is varied. So it's very interesting actually because you find everything. So there's already Hitchin and Tamish observed in their paper that higher components can have no wobbly elements because nothing flows down to them, right? So those are all very stable. Now for fixed points of type 2.1 and 1.2, you have the opposite. There are components where everything is wobbly. Then there are components where Drimfel's conjecture holds. In particular, always for type 1.1.1, it's either all very stable or pure codimension 1 or wobbly. And for type 2.1 and 1.2, it's either all. You have many things happening. You can have, there are some components of pure codimension. You can have all wobbly. And there's one special component in between, which corresponds to the Higgs field having a 0, which is precisely the criterion that hash, and ideal give for wobbliness in this case. And
So it's a rank 3 that you've analyzed only.
oh, the Bruno, right, yes. They also remark actually, they say it somewhere in the paper, I'm not sure in how much detail we've got to understand that.
Yeah, I mean, another question or comment? Yeah, so for the general case is, it seems to me that if you take a nilpotent with index the same as the rank, then you have some very nice flat that the quotient it would could be dimension 1 and it would could be more manageable. And it seems to me that you can apply also some inductive process.
When you say
Absolutely.
induction, you mean the length of the
Yeah.
inverted kernel?
Yeah, that is it. I mean, you have a vector bundle of rank n, then the index of nilpotent is n.
Mhm,
So then
Okay.
it's possible to have some splitting there
mhm.
and some induction in the same way that we did. Have you
For
tried?
length too, yeah, so I didn't know how to handle the fact that not all the iterated kernels are stable or not generically stable in an irreducible component. But
Yeah.
you say there's this disciplinary theory that can help them do that.
Yeah, then maybe, okay. Okay, any other comment or question?
Do you recall what happens at round 2?
Yeah, that's a good question. So in round 2, there is just one case. Yeah, so when, you know, in fact, I should have said this before. This is Pauli's work. From my team, I think. This is ranking. And many of the ideas are already there. So in round 2, what happens is that there's just the possibility for either the fixed field to square to 0 or to be 0. So in this case, you just have line bundles, right? So, so you have a 0, 0. And this is all. So what they do is they parameterize F1 F0. Okay, they have to belong to some symmetric powers of the curve, right? So these already have the information about the section. And then they need to parameterize over these the extension type of the vector bundle. So so then they are able, using the same kind of argument, to deduce which irreducible components are. I mean, this construction, the irreducible components were already constructed by Hitchin and Fagin in the 90s. So these were known, so what they look at is precisely where the Higgs field yields a divisor and spot all the Moduli divisor.
Seems you can do the same instead of line bundle, you take stable bundles.
Yeah, certainly.
Yeah.
That's what we use
Yeah.
for ranking. That's great.
What do you think? Any other question or comment? If not, let's thank Anna.